Thanks so much for coming today. I'm really excited to be part of this session and moderating this session. That's one of the benefits of co-chairing the program today is I get to choose the one session I'd like to moderate. And I chose to moderate this one, which is holistic approaches to reducing energy use in our data centers, which means everywhere from the server all the way up to the biggest cooling unit. So this is covering everything, which is really fun because often we think about when we think about reducing energy use in our data centers, we think about the cooling system or the electrical system. But we often don't always think about all the details down to the servers and within the rack themselves or the switching equipment or things of that nature. So we're going to cover a wide variety of those and how these two companies on stage with me today actually took a look at approaching their data centers in a very holistic way so they can reduce energy and everything. And this is part of one of the mantras that I have in all the work I do in my consulting practice is we always look at everything holistically. Never look at it as just one component or one slice. And that's how we accrue the greatest energy savings. So I'm really thrilled to have two great leaders in the technology space with us today, sharing their knowledge and wisdom from some data center upgrades that they made very recently.
We're excited to be here. We're excited to share with you what we have done at Facebook. Before I get into the details, let me share with you our company data center objectives. Our objective is to push the server operating envelope, improve the PUE, improve the data center efficiency, and save energy, basically. And if you're doing so, it's great. But anyway, that's our objective. And we share this knowledge with you, the lessons learned, the experience, and all that with industry. That's our. And if you look at this, the aviation and or nuclear industry, I believe that the reason why they have done so well in the last 20 years is because they share the data, they share the knowledge, they share the technology. And in the data center world, I'm not sure we're quite there yet, but I'm pretty sure that we can work together and beat this energy crisis. With that, let me explain what we have done here. Most of our data centers have a long-term lease contracts. And year 2009, we began looking for a ways to save on energy cost. Since the year 2009, we have done a lot of the server thermal test. We gathered a lot of data, and then we used this data to launch our first energy efficiency project. We chose this particular building because we're the sole tenant of the building. And when you're sole tenant of the building, it's easy to work with the landlord, easy to adjust the system as necessary, and without worrying about impacting other tenants in the building. This building, let me explain the pre-existing condition of this building. This building is about 56,000 square feet of raised floor, has a underfloor air distribution system, has a cryo units, but did not have the VFD, so it was very difficult for us to control the air in the data center. This data center had a water-cooled central chilled water plant, and no air or water side economizers. So there was no free cooling. And what we have done here is not a really rocket science. We applied very basic thermal theory and implemented 3 steps to reduce the cooling load. Number one, we contained all the cold dials, and so we can have a better control over airflow in the data center. Number 2, we raised the delta T across the servers by reducing the fan speed, the server fan speed. I don't know how many of you actually know about, you can actually reduce the fan speed by software firmware. You could do that. With that, we were able to reduce the number of cryo units in the data center, basically turn it off and save energy. And third, we actually raised the rack inlet temperature by raising the chilled water temperature. So after all this, this is what we have accomplished. We saved 2.4 million kilowatt hours of electricity, which equates to 276 kW in demand. And annual savings, $230,000 a year. And we actually received a nice rebate check from SVP, which offset it with our project installation cost. So this has been a really, really good project. Let me just explain quickly on this. This facility was about a 6 megawatt IT load facility. The IT load at the time when we were doing this project was 3.3 megawatt, which is about slightly above 50% loaded. And you see this UPS and PD loss was huge. The reason behind that is because a lot of the UPS modules were basically very lightly loaded. So if you look at the UPS efficiency curve, at like 9% or 10% load condition, the efficiency is about 70%. So that's why the loss was huge. Later, we'll show you what the changes that you see this PDU and UPS loss going significantly lower than the pre-existing condition. So the PUE was very hard to. I know you're gonna ask about the PUE. PUE was very hard to measure because at the time we were actually installing more cabinets, so it was very difficult to measure. But at that time, the number was like 1.87. At the end of this project, we were down to 1.58.
Thanks, Jay. So in the next few slides, we will go over what steps we took to achieve these savings in electricity. And if you want, we could come back to some of the graphs or figures that we have during our Q&A session. So first issue we tackled was inefficient airflow distribution throughout the data center. This data center is divided into 6 suites, and each of these suites has in-room cry units. And as Jay pointed out, many of these rooms were not fully loaded. So essentially, all the cry units were operational, and we were dumping a lot of air that we did not simply require. So we turned to our technology partners, and we installed the mesh of wireless sensors throughout the data center, and we gathered the data. We gathered the data for rack inlet temperatures, outlet temperatures. We had sensors installed underfloor to gather subfloor temperature and pressure data, as well as humidity data. And then we also did some CFD analysis to find out what exactly the effects are without cold aisle containment, and what the data center will look like, how it will operate once we put the cold containment in. And with that, we did put the cold aisle containment system in. These are some of the photographs, and we were able to eliminate the cold air bypass completely, which will so the cold air bypass was eliminated, so wastage was reduced, and also there was no hot exhaust air recirculating back into the cold aisle as a result. We also did some other things to seal all the sources of leakage within data center, the cable cutouts, putting the blanking panels at the bottom of the racks, and so on. Next thing we tackled was the servers. We analyzed all the data we had. We are collecting a lot of data as to the performance of each and every server, how they are reacting to the load, and how fans are spinning at that particular load. So with all that analysis, we came to conclusion that our servers were consuming more air than they should have. So we worked with our OEMs and we got them to help us optimize this fan speed control algorithm for the servers. As a result, the fans started spinning at lower speed, requiring up to 8 CFM less per server. That translated into savings of 3 watts per server in server fan power. So that way, we reduced not only the IT power, 3 watt per server, but we also reduced the demand on CRA units in room by 8 CFM per server. So say if a room has, say, 5,000 servers, it translates to at least 2 CRA units that could be turned off. And that's what our next step was, to shut down the CRA units. Again, we took help of the CFD modeling to run some what-if scenarios, how many CRAs can we shut down, and which CRAs are the best candidates for shutting down. We did those analyses, we found, okay, what are the zones of influence for each of the CRA unit in each of the room is, and also we looked at the data that we were collecting and monitoring in real time, and based on that, then we determined, okay, in each room, these are the CRA units that can be turned on, while keeping in mind that we need n+1 at all the time. Once we, oh, by the way, and we shut down about 15 CRA units throughout the data center, which resulted in 114 kilowatt savings in demand reduction. The next was raising the rack inlet temperature. And these are the graphs which I will come back during Q&A session or discussion session. But what we did essentially was we raised the CRA return temperature set points from 70 to 81 degrees Fahrenheit, and that way we got some savings there.
So raising the return air temperatures ties in exactly with the chilled water temperatures. So we have water-cooled chillers. There's a 2-step process, and this is a trend graph here that's just showing entering water temperature and leaving water temperature of our system. So the first stage is we shut off 15 CRA units. Originally, we have 44-degree entering chilled water temperature with a 10-degree delta T. After shutting off 10 CRA units, that turned into a 13-degree delta T that you can see on the graph. Then the second stage was raising that chilled water temperature. So it took 4 days to do in that. We raised the temperature on 2-degree intervals to just let it get to a steady state. So over 4 days, we raised it from 44 degrees up to 52, and that held a 10-degree delta T at the end. And the total system savings after seeing these changes is 171 ton-hours. This is a post-measure analysis graph here. There's a lot of data that we trended. Overall, it broke out to 2.4 million kilowatt hours, 276 kilowatts in demand savings. The CO2 emissions, what we cut down annually is 967 metric tons, which translates per the EPA standards to taking 332 cars off the streets and or 211 homes. You can see the IT load from the beginning of the project went from 3.3 megawatts up to almost 4. So that's about 600,000 or 600 kilowatts there. And then the cooling load actually went down slightly because we increased efficiencies in the air distribution and the chilled water systems.
And there you can see the UPS and the PDU loss was reduced quite a bit.
Right. So in summary, there are 5 energy retrofit methods that we took here. We did server fan speed optimization by updating the BIOS or the firmware on our servers, decreasing the demand for CFM. We did cold aisle containment, which also further decreased the demand of our CRA units. And since we don't have VFDs to be able to ramp down our CRA units, we just did CFD analysis to shut them down and gain motor energy savings there. And then we worked with our chilled water system, since again we're the sole tenant, so we were able to tweak that. And we elevated the rack inlet temperatures, and we raised the chilled water temperatures. And then with that, I'm going to hand it over to Jay for closing statements.
Yeah, so these 5 measures, I mean, I realize that not everybody can do all these five measures. If you're the colo providers, maybe you can do 2 or 3. If you're an end user like us, you could all do 5. But the point that I'm making is you can do something to save energy. So I hope you learned something today, and you'll take it back to your facility and come back with a greater project and share it with us.